Hey everyone, my name is Vedelin, and in this video we're going to learn the foundations of PyTorch, a library that is used throughout the industry for building deep neural networks and even large language models in production. We're going to start with what are tensors, what can you do with those tensors, and then we're going to continue with how you can use real-world data in order to convert it into a format that is usable within PyTorch. Then we're going to get the data and train a very simple deep neural network with it. And I'm going to show you how you can build your own model from scratch, and then how you can train your own model with PyTorch tools. Finally, we're going to evaluate the model, and I'm going to show you how you can actually create some pretty nice charts along the way. Let's get started. If you want to follow along, there is a complete talks tutorial that is available for MLExpert Pro subscribers, and you can find the tutorial within the bootcamp sections and then real-world PyTorch. In here you can find all of the explanations that I'm giving throughout this video, as well as all of the code that you need in order to follow along as well. Here I'm also going to give you some practical tips and tricks, so please consider subscribing to MLExpert Pro and enjoy the whole bootcamp if you're a subscriber. Thank you. I have a Google Colab notebook that is already running, and this one is using a T4 GPU, which is on the free tier on Google Colab. And the first thing that I'm doing here is to install Torch, and this is the latest version of, as of now, 2.21. So this is going to essentially install this on the Google Colab notebook that I'm running. And if you don't want to run on a Google Colab notebook, you can use your favorite Python package manager. For example, I'm using PyEnv, and within it you can essentially do pip install Torch, and this should give you the latest version of Torch. Of course, if you want to have GPU support, you need some sort of CUDA enabled GPU. So if you're having an NVIDIA GPU, this should be supported, at least if it is like, for example, 2, 3, or 4 years old, up to those years. And if you have installed CUDA appropriately. So if you have everything like that, if you go ahead and import Torch and look at the version of the library, you'll see something like this. And this will tell you that you're actually getting the version of Torch, but you're also getting this CUDA support. And if you want to have a look at why this is relevant, you'll see here that this is actually supporting the current version, which is 12.2, and here we have Torch installed with CUDA 1.12.1. So this should be supported, and in order to check that, I'm going to essentially do the following. So I'm going to ask Torch to see whether or not CUDA is available. And as you can see, this is returning true, so this should give us a nice overview or background on whether or not the GPU is actually running within the Torch environment right here. So the first thing that I'm going to show you is probably the most important concept of the PyTorch library, and those are the tensors. The tensors are actually something that I like to think of as data containers, and they can be n-dimensional. So for example, if you have just a number, for example 42, you can create a tensor of that, and this tensor is going to be representative of a scalar, and this scalar is actually going to be represented via a tensor within the PyTorch library. And unfortunately, PyTorch doesn't support working with, for example, NumPy vectors or just regular Python vectors. So in order to work with the PyTorch library, you actually need to create those tensors. And this is why you need to learn how to create them or how to convert other data formats into tensors, something that I'm going to show you how you can do right now. So let's start with the scalar that I'm going to show you. And the easiest way to create a tensor is to call torch.tensor, and you can just pass in the tensor or the scalar that you want. And I'm going to create a variable for that. And you can see that the output is actually a tensor of 42. So this is essentially how you can create tensors. So the next thing that I'm going to show you is how you can get the internal value of the tensor. and I'm going to call just item, and this will essentially return an integer that is the wrapped value of the tensor that we have created here. This is very important if you want to get the value of the tensor and convert it into something that Python or NumPy can actually understand. So the next thing is to actually check the type of the tensor. You might know that Python is actually, let's say, very loosely typed, and even though if you're passing in an integer or something like that, you don't really care about the type of this number or string or whatever. But in Torch, you actually need to care about the types, and you have some ways to convert from different types to other types. For example, from floats to integers, or from floats to strings, or etc. So another important thing that I forgot to mention is that actually tensors don't really work with strings. And let me show you what I mean by that. You can't actually create this tensor with a string. So in general, you need to think of tensors as containers of numbers. And those numbers can be of different types, but pretty much strings are not allowed here. And pretty much every time when you do something with neural nets or other models, you don't really or can't really work with strings. You need some way to convert those strings into numbers. So keep that in mind. So to check the data type of our scalar, I'm going to call just a property called dtype, and this will return to us torch.int64. So one important thing about this is that the default representation of this integer is int64. This is chosen when the torch tensor is created automatically for you. And another important thing is that this is not just an int or any other type. This is type that is specific to Torch, and it's called torch.int64. And if I call this, I'm going to show you. Actually, this is the self-representation of this type that you have. So how can you use this in order to convert, for example, this integer into a float number? So one thing that you can do is to create or call the method to. And for the scalar, I'm going to use float32, and I'm going to create a variable for that. I'm going to print out the value, and then I'm going to print out the type of this scalar, new scalar. As you can see, the type now is float32, and this is the representation of the item. You can see that this is now a floating point number, and if I do call the method item on the float tensor, you see that we have 42, but this is now a floating point number. Something that is very important if you are, for example, getting some errors that are saying, well, we expected here to have an integer, but you're giving us a float, or vice versa. This is pretty much a surefire way to do something along these lines, and then PyTorch will probably work fine after that. This is very common when you're passing, for example, some features or some labels during your trainings, or maybe some loss functions, etc., and then doing some calculations on those. This is pretty common to get an error that the types are mismatched, and then you probably need to do something along these lines in order to convert into the correct types. Yeah. So next, I'm going to show you how you can create a vector, and this will be very easy to do. Again, I'm going to call torch.tensor, and I'm going to pass in two numbers in here, and I'm going to pass in those numbers into a Python array. And let's have a look at what we get from that. You can see that this is now represented as an wrapped array or list in Python within the tensor again. And if I call the dot shape property of this one, you see that we have 0 for first dimension, or just a single dimension, and within that dimension of the tensor we only have two elements. So this is the shape of the tensor. This is very similar to what you have in NumPy. So if you're familiar with that, this should be pretty much exactly the same thing, except that instead of a tuple, you're receiving this torch.size structure, if you will, which is going to be representing the dimensionality of each axis for your tensor. Since tensors can be n-dimensional, you can pretty much understand that this is going to be representing each dimension size. Another thing that you can do right here is to call vector.dtype. Let's see what we have. And this is essentially the type of each element right here. Let's try something. What will happen if I'm essentially creating this? Will this work? Yeah, it works. But as you can see, PyTorch is automatically converting the integer value into a floating point number. So essentially what you can't do is to create a tensor with different types within. So let's say that I have this. Again, this will convert the 42 into a floating point number. So essentially Torch is doing some smart stuff behind the scenes, but you need to have the same types within the tensors. Okay, so another thing that I want to show you is how you can create, for example, a matrix. And in this matrix, I'm going to essentially create this vector here. I'm going to take that for the first row, and then I'm going to essentially reverse that into a second row of the matrix. Yeah, so now the current matrix have 2 rows with 2 columns. This is a square matrix. And if you call the matrix.shape, you see that again we have the 2 dimensions for the rows and the columns of this matrix, if you will. And then in each dimension we have 2 elements. And if I try to, let's say, put in 3 right here, we'll get an error since the first array or list is not exactly the same as the second one. You can essentially do that with the matrix, and PyTorch will not allow it as well. Tensors are great stores of values, but in order to do something useful with those, you need to learn how to create operations on them, or how to use those tensors in order to produce something that is usable. So in order to do that, PyTorch allows you to use a lot of operations on those or methods on those. So I'm going to start with some helpers that I've used pretty much every time that I do some, let's say, much more fundamental research. And in order to do that, I'm going to show you a couple of helper or very useful functions that I use. So first one is torch.zeros. And in here, you can create a tuple. And this will essentially create a matrix or other type of tensor depending on the dimensions that you're given in with zeros. So for example, if you want to initialize some dummy variables, or say for example weights or something like that, you can use this in order to get a shorthand of how to create a tensor with zeros. Again, you can have torch.ones to create the same thing but with digits of 1. And another thing that I like to use is torch.around. And here for the size, I'm going to pass in something a bit different. And this is the tensor that you're going to get. Those elements are going to be small numbers between 0 and 1. And for each one, you're going to get essentially a random value. So this works as expected as well. And again, another important thing that you can do is to create this reshaping. So for example, if you have, let's say, this matrix with 2 rows and 3 columns, and you want to convert that into, for example, 3 rows and 2 columns, you can use something like that. I'm going to create a tensor here. with 1, 2, 3, and then 4, 5, 6. And if I want to reshape this with 3 rows and 2 columns, you see that the new tensor is actually reshaped correctly when I call the reshape method on the tensor that we've created. So another important operation that I do is to essentially remove some dimensions, if you will. So for example, let's say that I have the tensor 142 and then 42, 1. And if you have a look at the shape of this tensor, you see that it is 2 and 2. And if I want to add another dimension on this, I'm going to call unsqueeze because mostly when you're doing operations on tensors, you can't really do those operations if the dimensions don't match. So for example, if you're multiplying matrices or vectors, you essentially need to have the correct dimensions in order to do the operations. So unsqueeze is essentially adding another dimension on top of the tensor. And if I do this on dimension 0, and have a look at the shape. Sorry, I probably have a typo here. Yeah. Unsqueeze. You can see that we've added another dimension. And if I remove the shape from here, you're going to see that essentially what we did here is to add these new brackets, which allow us to give us this new dimension. So I'm going to leave this. Again, this is pretty useful when you're working with different types of tensors. So let's say I have a tensor that is created like this with 2 rows, torch tensor, and in it I have 2 rows of a matrix. And let's say that I have the numbers 0.3, 0.5, 0.2, and in the second one, 0.1, 0.05, and then 0.85. So essentially you get this, and both of those rows should sum to 1. So this is our example. And if I have to get the maximum value from all of these, t.max will return the maximum value from all of the tensor values. And if I want to return the maximum values for each row, I can do t.max, and for the dimension, I want to specify the first dimension. So if I show you right here, the dimensions. So this is going to be the 0th dimension for the 2 rows, and then for the all of the elements, it's going to be the dimension 1. So if I do this, this is going to return 0.5 and 0.85. And if I do the first dimension, this is going to be essentially returning each of the column maximum values, something that we don't really want in our case. So let me just do this. And note that the maximum value is going to be returning just the values and then the indices of those values. So this is really helpful if you want to get the elements themselves or the positions of the elements themselves. Most of the time, you are not going to be creating tensors from scratch, and you will probably use something like NumPy arrays, pandas, or just Python lists. So in order to do that, Torch is providing you a lot of helpers in order to work with those. And let's say that you can do something like this, or you have something like this. For example, if you have a NumPy array, and I'm going to add NumPy in here. And let's say that you have this NumPy array, 1 and 42. So this is the array that you get. And then in order to convert this into a tensor, you need to essentially call from NumPy, pass in the tensor, or the NumPy array. And again, if you just call the A, you see the array, NumPy array. And if you call t, you will now have a NumPy, a tensor from NumPy. So this is really useful when you do such operations and your arrays are probably in NumPy. Of course, you can pretty much do the same thing for pandas, but it is a bit more involved since let's say that Torch doesn't have a direct integration with pandas, while the integration with NumPy is pretty good. And let's say that we have this data frame. I'm going to create a data frame with a single column, 142 for numbers. And let's have a look at what we have here. Yeah, you see that we have this very simple data frame. And in order to create our tensors from that, I'm going to create torch.tensor. I'm going to call the numbers, and then I'm going to call NumPy. And this is essentially the second way to create a tensor out of NumPy array. So you see here that I'm actually converting these are the numbers. Oh, that's great, actually. We are getting a preview of the plot of the numbers. Great. So this is essentially one way to convert the array into NumPy arrays from this series, the number series of the data frame. And then I'm going to pass in that to Torch tensor. And let's see if we call this from NumPy, essentially get the same result. So this is a way to create tensors from data frame. One of the most important advantages of using PyTorch is to actually run your operations on a GPU. And this is significantly speeding up your computational performance, of course, depending on the GPU that you have. And in here, again, we're using a T4 GPU. So let me show you how you can essentially put some tensors on the GPU and run some operations. So the first thing that I've already shown you is to check whether or not this is available on your PyTorch installation. And this is the CUDA enabled acceleration. And you can see that this is actually true in our case. We have the correct PyTorch version with the correct CUDA installation, and then we have a GPU that is also available for us. Next, I like to do something like NVIDIA SMI, and then I'm going to query the GPU memory used. And I want this into a CSV format. And as you can see right now, we have just a 3 megabytes of memory used on the GPU. And let me get the device that is going to be pointing to the GPU device from the torch. So this will essentially give us a pointer to where we want to store our tensors and where the calculations are going to be carried on. So I'm going to use a CUDA device if essentially we have the CUDA implementation. Else I'm going to use a torch device CPU. And this simple if is going to be run in order to get the device that we want. And now, up until now, at least, if we call t.device on our previous tensor, you'll see that we get this type of CPU right here. And if I do something along the lines of this, create a GPU tensor variable, and then I'm going to use the same thing that we've used before, torch.tensor, and I'm going to pass in an array, and then I'm going to say device, and I'm going to pass in the device. And if I have a look at the tensor now, you see that before we didn't have this device part, while now we have the device part on CUDA 0. So this is going to be essentially storing our tensor on the first available GPU with index 0. So you might guess that if you have multiple GPUs, you can essentially pick and choose where your tensors are going to be stored or on which one of the many that you have. And in our case, we have just one. So this is going to be essentially pointing on this device. And again, if I call GPU tensor.device, you can do that. And let me experiment with CUDA 0 right here. And now you are essentially getting the complete index on the CUDA device. So if there is the case that you have multiple GPUs, this tensor is going to be specifically put in the zeroth device. So again, I'm going to query the GPU memory usage now that we have a single tensor on the GPU. And you can see that not the single tensor, but since we're using the PyTorch on the GPU right now, you can see that we've bumped this to 100 megabytes more. Of course, this tensor alone does not do the damage, if you will, but all of the necessary requirements or implementations on PyTorch are going to be put on the GPU, and this is going to increase the memory usage that you have. So this is perfectly normal. So let's say that you have a CPU tensor or a tensor that we've already created. So I'm going to get this. This is our CPU tensor. Pretty standard, something that we've already worked on. And again, this is not stored on the device. That is going to be the CUDA device right here. So in order to put this tensor on a GPU, we are going to be using the same two method that I've shown you previously, but instead of the data type, here I'm going to pass in to device. And let's have a look. You see that the device now is CUDA 0. So this is going to essentially be putting the tensor on the GPU. So this works as expected. All right, so let me show you something a bit more interesting. What happens when you do something like this, CPU tensor times GPU tensor? So these tensors should be able to be calculated, or the response for those, but this is the error that you're getting. Essentially what this says is that you need both tensors to be on the same device, but in our case we have a CPU tensor, which is of course on the CPU side, and then we have a GPU tensor. So what you can do in order to complete this, let's say that you want to put in the CPU tensor to the device, which is going to be the CUDA device, and then I'm going to multiply this by the GPU tensor, and now you have the calculation result that is pretty much giving you this tensor right here. And as you can see, the resulting tensor is also on the device that you wanted, or that you set, which in our case is the CUDA device. And if I do something like the following, if I get the CPU tensor, get the GPU tensor to be on the CPU, you now see we have the same result, but this time the tensor is not on, the resulting tensor is not on the GPU. So you do need to have in mind that you need to essentially manage this process if you're only going to be using PyTorch. For the next part, I'm going to include some imports right here. These are pretty much going to be helping us with various tools. For example, the order-dict, some typing implementations, matplotlib. And then for the torch, I'm going to import NN, the atom optimizer, which we're going to use in a bit, a data loader and a dataset, and then TKDM in order to follow the progress of our whoops. Another important thing that I'm going to show you here is how to set the seeds for your random number generators. And this is for the random library in Python, then for NumPy. And finally, I'm going to use the manual seed function or method from Torch. And here I'm going to set the seed to 42 for all of these. And once those imports are complete, I'm going to go down to the notebook. and I'm going to download a CSV file that I'm going to show you the contents of which right now. So let me start by calling this, for example, data wrangling. So when you deal with real world data, for example, you might have something like this CSV file, or let's say something from a database, from SQL database, or other type of data. For example, it could be API response or something like that. The first thing that you need to do is to get this data to be into something that you can understand from PyTorch. So this is the data that I have. This is from Kaggle, and it represents a lot of data on calorie expenditure based on some activity for different users. And this is the user ID. And then you have all of those metrics for these particular minutes, sedentary minutes, active minutes, fairly active, very active, etc. And then how much calories were expended based on those activities. If you want to have a deeper look at the data, again, go to MLExpert Pro, to the MLExpert Pro tutorial, in which I am explaining the data in a bit more depth. But again, this is from Kaggle. And in order to get these, I'm going to these header names, I'm going to be using this pattern in order to put them into something more nicely along the Python lines. So how can you use this data frame and convert it into a PyTorch data? So for that, I'm going to be showing you how to convert this into PyTorch datasets. And first, I'm going to take the unique users. To do that, I'm going to get df.id.unique, and this is going to return a list of all unique user IDs. Yeah, I have a typo here. Okay, now that we have the user IDs, I want to get different users within a train, test, and validation splits. So in order to do that, I'm going to be using the train IDs, temp IDs, using the train test split function from skwarn. And the test size for that is going to be 0.2. So 80% of the data or the users are going to be reserved for training. Of course, this is not a lot of data, but yeah, we have some examples here. And another thing is to get the test IDs and validation IDs. And pass in the temp IDs. And for this, I have test size 0.5. So essentially what those are going to be the train, test, and validation IDs of the users. And each user is going to be in a different branch or a different subset of the data. So to get the actual data for those, I'm going to filter by the IDs. And if I do isIn, this should give us, let me just check here. Yeah, this should work. Train, test. And then val for the validation. All right, so it looks all right. Let me check the shapes of each one. All right, so we have 15 columns for each, 70-30 examples for the training data, 87 for testing, and then 123 for validation. It appears to be the case that even though we have the same number of users for test and validation, different types of users have a lot more data compared to others. So this is something to be expected. And Now I'm going to continue with how you can get essentially this data frame and convert it into something that PyTorch can understand. So in order to do that, I'm going to extend the dataset class from the PyTorch library. And I'm going to create a class called calories dataset that is going to extend the dataset class. And essentially what you need to do here is to have a get item method, which is going to take an index, and then have a len method that is not going to take anything except for self. And these are the required methods that you need to override in order to build this dataset. So I'm also going to add a constructor here. And this is going to take a data frame. So in order to have a look at what we need, I'm going to go back to the training df and have a look at the data that we have. So in here, I'm going to be using just two columns for the features, total distance, and then very active minutes. Yeah, I believe so. And then I want to get the calories. Maybe you can do some combination of all of the minutes or something like that, because very active minutes can be a very low number. But yeah, you can use these in order to create the calories, or have a look at how the calories are essentially expanded. All right, so in order to do all of that, I'm going to create a features property of the dataset, and I'm going to take in the total distance and then the very active minutes. And then for the labels, I'm going to take the calories. So for the length or the number of elements within the dataset, I'm going to essentially return the length of the labels. And then for the item, I need to be converting these into tensors or integers. So for the features, I'm going to create a float tensor. And in this float tensor, I'm going to be creating something along the lines of getting the features at the index position. And then I'm going to convert these into an NumPy array. This is going to be the floating point tensor that we're creating. And then for the label, I want this to be from the labels, and I want this to get the label on index that is given to us. And finally, I'm going to return the item, which is going to be the features, and then the label. Let's run this. All right. So let's have a look at what we have. If I create an instance of this dataset, calories dataset, and I pass in the train data frame, and I get the first element of this dataset, I have a type of float tensor, all right. And you can see that we get this tuple, which contains the features floating point tensor with a vector in it. And then we have an integer that is this label right here. So essentially what you get is the features and the label for this particular item. So this appears to be working quite fine. Then I'm going to create test dataset. And then validation. Let's actually reverse those. All right, so we have the three different datasets. And now I'm going to be wrapping those within data loaders. The important thing that data loaders are doing is to actually create batches in order to train your models much more efficiently. So instead of getting, for example, just a single example per iteration when you're training your models, you can specify a batch size, which is essentially the number of examples from the dataset that you can use during training to significantly speed up your training, of course, and probably this is going to be giving you also better models overall. But if you want to choose this batch size, you can essentially need to wrap your datasets into data loaders, and this is pretty easy with PyTorch. So train data loader, I'm going to create an instance of the data loader, and in here I'm going to specify the dataset. In our case, train dataset. I'm going to specify the batch size equal to 8, and I want this to be shuffling the data, and then number of workers, which is essentially the number of threads that we are going to be using in order to load the data. And final parameter is drop last equal true, which is going to essentially give us a data loader that has batch size of each batch size have exactly 8 examples. And if you don't want that, you can remove this. Shuffling, this will essentially give us the shuffled results from the dataset. This, of course, is going to be break any dependencies based on the user data. And then for the validation loader, I'm going to be essentially doing the same thing. Let me just copy and paste that with, of course, some differences. We are not going to be using the train set here, and I don't want this to be shuffled. All right. And then exactly the same thing for the test loader. And we don't want any shuffling within the validation and test sets since we don't really care. You can actually shuffle it, but it's not needed to, because the data there shouldn't provide you with feedback in order to evaluate your models further. All right, so let's run through this. Sorry, you don't really care because you don't use the errors or anything to improve your models. Of course, you can overfit on your own if you're training the model multiple times with some of the data. So yeah, you might try to shuffle it, but essentially this is what I do. So how do you get a batch of this loader? I'm going to get the features and the labels, and I'm going to enumerate on the training loader, and I'm going to print the features, print the labels, and I'm going to break because I just want this to have a single example. And you see that this is actually returning the tensor with the features. Are the first 8 examples with the very active minutes and total distance and very active minutes. You can see that we have a lot of zeros right here. So again, you might want to try to do something a bit different. Maybe select other features, do some feature engineering. This is not the point of this video, of course. And these are essentially the labels. And one important thing right here is to see is that the actual output of the labels is now a tensor. So there is this batching function that is essentially doing the loader's job in order to give us tensors for each. And as you can see, your integers from the labels are actually converted into a tensor that is a batch size with the batch size of 8 with elements that are again integers, but those are wrapped within a tensor. Now that we have the data converted into datasets and data loaders, we can continue with building a model. And in order to do that, I'm going to be using the sequential method of building PyTorch models. And this one is very nice compared to other approaches, such as extending an NN module or creating a module dictor list. And I like this approach when I'm building somewhat simpler models, such as the one that we're going to create right here. And in order to create the model, I'm going to be using nn.sequential. And in here, I'm going to pass in an ordered dict, which is going to take array. And within that, I'm going to pass in some tuples. For the first layer, I'm going to call it a hidden layer 1. And this is going to take a linear layer. So if you don't know what a linear layer is, it is pretty much a fully connected neural network layer. And this one pretty much requires to have a number of features for the inputs. In our case, we have only 2 features. I'm going to pass in 2. And then as an output features, I'm going to specify 64. And this is a place where you decide how much elements or weights or parameters you want your neural network to have. And this is some sort of experimentation with trial and error in order to get better results. Of course, with some experience, you can choose those as well, find those more easily, is what I mean. But I like them to be some sort of power of 2. Of course, this is not strictly required, but this is how I found those to work really well. And then I'm going to pass in an activation function. In our case, I'm not going to be using anything crazy, just a revo function, which is going to be actually breaking the linearity of our neural network. And this will hopefully increase the performance of our model. So next, I'm going to pass in a hidden layer, next hidden layer. And in this case, I'm going to pass in the number of input features, which is going to be 64. This should be the same number that we had before. And then I'm going to reduce the number of parameters to 32. I'm going to get this and do activation 2. Again, a revo function. And then I'm going to create another layer called output layer. And this is going to be taking this 32 and it is going to output a single number, which is going to be the number of calories that we are predicting. And this is pretty much the model that we have. And if I have a look at what we got, this is essentially the model representation. One great thing of the way that we've initialized the model is that we pretty much named each layer. And of course, this is really useful when you are having a look at the model itself. This is pretty nice representation of what we had right here, and it is pretty readable in my opinion. So this is why I really love this way of building models. Of course, this is not so, let's say, extendable, such as when you're extending from any module or something like that. But in simpler cases, and this is pretty much amazing since I love how easy it is to read these types of codes. And then the output is really nice to understand and easy to understand as well. So let me show you how you can actually query individual layers, hidden layer 1, for example, and then I can get the weights. And for that, I can also call the shape. So you see right here that the shape is actually corresponding to the input features 2, right? This for the input features, and then the output features is going to be 64, this shape right here. And if I go to the next layer, you might expect 64 and 32, exactly the same. So this is essentially a representation of the weights that you have or the parameters that were initialized. And if you take a look at some of the weights, you see that, for example, let's go to the first layer right now and take just the first 10 examples. You see that these are the initial weights that we have from our model, since those were created by these constructors right here, and they were initialized internally to some very small random numbers. As you can see, nothing is quite large or nothing is quite negative. So you see those numbers are initialized with some default initializer. And then I'm going to take a bit of code in order to show you what we can also do with our models. So this is going to be essentially creating a data frame for us with the layers, and I'm skipping the activation layers right here. Maybe you can also include those, but yeah, these are the representations. You see that we have weight parameters of 128, so this is exactly 2 times 64, and the number of bias parameters is actually the number of output features. You can see for the next layer we have 64 times 32, and then 32 as bias parameters. Exactly the same thing for the output layer. So this is again a nice way to represent the architecture of your model, and I really love to do that. This gives you a way to summarize what your model architecture is. For example, if you have something like very much larger, like BERT or TinyOne or something like that, you can do such visualizations, if you will, and understand a bit better what is behind this model that you're having. Of course, when you go to something even like TinyOne or something like that, it is very, very hard to understand the complete architecture of the model. But with some smaller parts of those models, you can get a pretty good feeling of what is happening behind the scenes, or what are their implementations actually in PyTorch. So in order to have a look at the predictions of this empty model, or not so empty but untrained model, I'm going to iterate over the data loader, the training loader that we have, for the features and labels, and enumerate on the training loader, as I've already told you. And in order to get predictions from the model, I'm just going to call it as if it was a function. And this is going to be passing in the features. Keep in mind that the features in our case is actually a batch size of 8. So let me just show you that. Something that is particularly important when you're working with PyTorch. Yeah, so we have 8 examples, and each example have 2 different features. And if I actually run the predictions, you see that the model is actually handling this. So what is happening behind the scenes is Torch is just fine with passing in features that are actually in batches. So it is expected that the batch size is going to be 8. So even this help here is telling us that this is actually the case. So PyTorch internally is allowing the batch size to be run through here. And let's have a look at the predictions. And yeah, you can see that the predictions are quite bad compared to the labels that we have in the batch. Yeah, but we'll see that after some training, these are going to be improved much more. Now that we have a model, let's continue with how to train the model itself. So I'm going to get the training in here. And one of the first components that I want to have is a loss function, which is going to be used in order to essentially evaluate how well the model is currently doing. And in our case, I'm going to be using a Huber loss. And this loss is quite good at navigating between very large losses and very small errors and very large errors. Since you might have a look at the fact that the actual calories are very large numbers, and one way to escape from that is to do some scaling of the labels and the inputs. But in our case, I'm just going to train the model as it is. So in real world examples, scaling might be very advisable right here. But this will be besides the point of working PyTorch. And then the next component is going to be the Adam optimizer. In our case, we're going to be using these optimizers to update the parameters based on the loss function and essentially make us model learn better over time. And this one is going to be taking a learning rate of 0.001, which is essentially the default value of it. And then I'm going to get the model and pass it to the GPU device, since this is where I want the GPU or the training to be happening. So these three are actually the components that we need in order to start the training process. And for the training loop itself, I'm going to be running this training for 100 epochs. So what this means is that our model is going to have a look at the training data or the full training data for 100 times. I'm going to store the best validation was, and this is going to be minimized over time. I'm going to also save a state of the best model. Next, I want to store the training losses on the training data and then the validation losses in arrays. And then for each epoch, in the number of epochs, I want to do a couple of things. First, I'm going to calculate the training loss using train one. I have a typo here. Train one epoch function, which I'm going to show how we are going to write in a minute. Then I'm going to pass in the train loader, was function, optimizer, and then device. Then I'm going to get the validation loss, call the validate function, which again I'm going to write in a minute, with the validation loader, was function, and then a device. And then if our validation loss is smaller than the best validation loss thus far, we're going to update the best validation loss. You know how to pretty much write a minimum function. All right. And then I'm going to also get the best model state to be the copy of the current model. All right. And then I'm going to simply append the train losses and the validation losses right here. Of course, if you run this right now, we don't have the next two functions that we need. But overall, this is the flow that I'm going to be using in order to train the model. We are going to train the model on one epoch of training data, validate on that. And if the validation loss is better compared to what we had before, I'm going to store it. And then I'm going to also store the best model. Also, I'm going to store these values in a sort of history for the training losses and validation losses. And I'm going to show you why we're going to need that in a minute. So next I have the validate function and then the train one epoch functions. Let me just copy and paste those since it will be a lot of time in order to write them in here. So this is the train one epoch function. So in here we are essentially using the training loader, iterating over the features and the labels, putting them on the device that is passed in. In our case, this is going to be a CUDA device. Then I'm zeroing out the gradients on the optimizer. This will ensure that the calculations for the was function are correct. Then I'm using the widgets model features. I'm predicting the outputs based on the features or the current features. I'm then removing the widgets. I'm returning the first dimension of the widgets, or these are the predictions, the widgets. Then for the labels, I'm converting him into a floating point number. So this is somewhere where converting those to a floating point number will allow our was function to do calculations correct. And after the calculation is done on the was function between the widgets or the predictions and the labels that we have a was function. Then this was error or function result is going to be propagated back to the model using the was.backward. Then we are advancing the optimizer. And this essentially is going to update our model's weights. And then we are calculating the was currently. And we are multiplying that by the size of the features that we have. And this is accumulating within this variable. And finally, I'm returning the average was thanks to the accumulated value and division of that by the O of the elements within the dataset. So this is how we calculate the training was. And then we have another function which we've called validate. And I'm going to show you the contents of that. It's a bit more simpler. So here we started with model train, and then in the validate, I'm putting the model into evaluation mode. And I'm calling torch inference mode. This will essentially turn off any gradient calculations, etc., and probably will speed up the inference times for your model. We are going through the validation order, then do exactly pretty much the same thing. Then getting the predictions, calculating the loss, and accumulating. Note that we are not using a zero gradient or any optimizers or backward propagation here, since we're just evaluating the model this far. So I would say this is a stripped out version of the train one epoch function. And let's see if this is actually working. So you can see that the training is actually happening, and it's not extremely fast, but it appears to be working just fine. So the training took roughly a minute in order to complete. We did 100 epochs with that. And then for the next part, I'm going to show you how you can get a feel of how well the model is doing. So the first thing that I'm going to do is to plot the train and validation losses. So I'm going to be calling pot.plot on the train losses. And then pot.plot val losses with a label of validation. Then I'm going to label the loss on the y-axis. And on the x-axis, I'm going to be labeling epoch. And then I'm going to call a legend on that. And this is the result of the training. You can see that this chart is actually showing us for each epoch how much each value of the losses were. And you can see that the validation loss has pretty much stayed flat after, let's say, 40 epochs, but the training loss kept on lowering. So this is something that you might have troubles with if you keep the model lowering the training loss, but the validation loss is pretty much staying the same or even starting to go up. This is known as overfitting. Even though the model is remembering the training data, it has a lot of trouble with the predicting on new data. So this is essentially what is happening here. Will be happening here if you, for example, continue training this model, probably. Not really, I can't really be sure about that. Another important thing to note here is the fact that you might have a look at the fact that the validation losses, let me show you, the minimum of the validation losses is this number, while the worst validation loss is, let's see, a bit higher. So the minimum validation loss is probably somewhere where your model is going to be perfect. So this is why we essentially took the best model state and stored it into a variable. So in order to load this model, I'm going to be creating this variable called best model and going to copy the current model that we have. And on the best model, I want to load the state dict of best model state. And this will essentially get the parameters and match them with all of the keys. And you are getting these types of message. This means that you're doing the correct thing. So this will pretty much verifies that we're taking the model, copying it, and then loading the state dict of the best model and the parameters along that. So let's have a look at how can we get some predictions from our model. First, I'm going to be putting the model into evaluation state. and I'm going to take the predictions, and then I'm going to save all of the labels, and recall that I'm using Torch inference mode to somewhat speed up the inference, and I'm going to iterate over all of the examples within the test folder. And I'm going to call the model with the features, and I'm going to pass in the features to the device, which is going to be our CUDA device in our case. And for the predictions, I'm going to append those into the list that we get. And for the labels, I'm going to again take the labels and create a list of those. You can see that the inference is actually quite fast. We have just 10 examples with the batches. So again, this is pretty fast. Let's have a look at what we have in a prediction. So compared to what we had with the untrained model, you can clearly see that the numbers are now anything like 0 or 0.1 or something like that. Those numbers are much more improved now, and you can see that the model has at least warned something, and we have to check whether or not this something is actually something that can be useful as a prediction. So let me just get all of the labels that we have and convert them into a list. So this will essentially merge them into a single tensor, flatten it into a list, and get the labels list. I'm going to essentially do the same thing for the predictions, since they are also in a tensor. Yeah, let me check the labels and the predictions length, just to make sure that everything is all right. Yep, 80 examples for each. And then I'm going to show you plot of the results. I'm going to paste it in, so it's going to be a bit simpler to understand. I'm going to essentially create a scatter plot between the labels and the predictions. And this is something that you get. So on the y-axis are the predictions, and then the true values or the labels are over the x-axis. And you can see that the model is predicting most of the values very well. As long as you're along or very close to this value, you're doing a pretty good job. But we have some examples that are very far off. Their predictions are very far off compared to the real or true values. So this might be a room for improvement. There might be a room for improvement in order to create better models, or maybe choose better features in order to predict those types of examples. So this is it for this video. We've seen how you can get started with PyTorch, at least the latest version of PyTorch thus far. And we've seen what tensors are, how you can do some operations on tensors, and how you can get some real-world data and use it in order to train your own models from scratch with PyTorch. Thanks for watching, guys. Please like, share, and subscribe. Also, join the Discord channel that I'm going to link down into the description, and I'll see you in the next one. Bye.